All right, welcome to the final exam review. If you're looking at the video, yes, this is extremely awkward for me because there's nobody in here. That might change randomly throughout the video. We will see. So for the exam, it's going to be 10 true, false, 10 multiple choice questions for problem solving. So some of these true, false, multiple choice you will have seen before. I will take some of the more wrong questions from previous exams and they will be back. For the problem solving question this time, they're going to be 20 points instead of 15. So they will be a little bit lengthier in that regard. It's going to go live Tuesday at, sorry, not 12 a.m., p.m. So noon, and it's going to close midnight on Friday. So you'll have those 36 hours. No late exams will be accepted. Closed notes, closed internet. You can use an equation, your own personal equation sheet if you want to, but that is different from notes. So if we look at the course competencies, these are the two that are related to lecture material. I did not put the two associated with labs in here. So if we look at what the competencies are, right, we have network theorems. Those were superposition, Thevenin, Norton, mesh, node, loop. All of those are considered network theorems. So we'll talk about that in a little bit here. Phasors, so that is our imaginary stuff. So we've been using that in conjunction with RL and RC circuits more so. With RLC circuits, we're just utilizing those second order differential equation solutions. So phasors and first order differential equations, that will be an RL circuit problem. So you'll have one of those. Dependent sources will be in the multiple choice part of the exam. And then for our second order circuit, you need to be able to understand how to read those tables and go through and do that. So you'll have the RL and the RC circuit to go through, or sorry, the RLC circuit. So identify if it's series or parallel. Once you have that go through, you'll be tasked to show how you know what type of damping it is, and then from there, figuring out that equation. So with the material, I got asked to go over the branch loop and node method. So you will have a question that has you going through and doing this. I will not ask you to specify for going through and solving, but exam 2 number 1 was kind of similar to this. For that one, we superposition was the best method. That will not be the case for the final. So I'm going to go over these methods here and see. So for branch current method, this is where we're going to go through and we are going to create two different, in this particular type of circuit, you might have an extra loop, but here, right, we have our two different loops. So going through and doing this, we're going to look at Kirchhoff's voltage law and Kirchhoff's current law to go through and do these. So any loop is a complete current path within a circuit. So you'll start and end at the same location. So if we're looking at this here, R2 in the middle, that is going to be shared between loop 1 and loop 2. So we would need to make sure that that is being applied correctly. All right, the node is where two or more components are connected, and a branch is any current path. So if we're looking at the left here, right, all of this shares one current value. And then if we look at the right, everything over here shares one current value. And in the middle, you would have a second or a third current value here. So when you would go through and have this type of circuit, it is very beneficial to go through and label things. Keep that labeling method. That way I know what you are doing. So the branch current method is an analysis method that relies on Ohm's law and Kirchhoff's laws, so loop and voltage, to go through and find all of the different unknowns. So what you would go through and do is you would pick a direction for your loop. So in the case of these here, you might want to do it in the direction of the conventional current from the battery, so out the positive end. That would probably give us the simplest solution. Show the polarities of the resistor voltages according to the assigned branch current directions. So for resistors, for a current, we have it typically going from positive to negative by Kirchhoff's voltage law. So delta V equals 0 by Kirchhoff's current law. So that is current in equals current out. And with this, we would typically have a system of equations that we would need to go through and solve. You can do this in whatever method you want. So you can do it through substitution. You can go through and do it with determinants. If you are doing it with determinants, typically that means you guys are going to be plugging it into your calculator. Please write out the determinant that you are using. So you should show the equations that you've created. Show the determinant that's going to give you the most possible, or show the matrices that you're going to use. That's going to give you the most possible points to go through. And if you mess something up in your calculator, you'll not have anything. So I am going to have you, part of the question is going to be writing out your equations for the question that's going to be one of these methods. So go through, identify those equations, then show the matrix and plug it in. You're going to do it through substitution. Consider labeling your equations so I can follow along with what you're doing. And then you're going to be able to go through and solve. For loop current method and with the node voltage method, these are a lot more specific for how we're going to go through and utilize them. So with the branch method, you're kind of mixing Kirchhoff's voltage law and Kirchhoff's current law. With the loop and node methods, you are sticking to only one of them. So the loop current method is also referred to as the mesh current method. In this case, you're going to go through and apply the voltage law through all components of the circuit. So in this case, we would go through and we would have our two currents. And from here, for each of the different currents, again, typically when we would do this, we would choose all clockwise or all counterclockwise for our current values. This would mean that for each resistor, we're going from positive to negative, and we would need to take that different signage into account when we would go through and utilize the voltage law for these loops. So typically clockwise is used for the direction. You can do counterclockwise. I just am going to recommend that if you are using the loop current method, that you are going through and you are picking one direction to go through and do it. If you want to go through and use arbitrary directions, I would recommend using the branch method in that case. Then indicate, right, your voltage drop polarities based off of the current, so drawing in those positives and negatives. Kirchhoff's voltage law to go through and solve. Each equation is going to give us one current. Again, for going through and doing this, you'll have to write out all the equations that you're going to be using. So do that. And then if you're going to plug it into a calculator, at least show what you're plugging in some method. So substitution or determinants, both should be fine. Node voltage method. So again, a node is the junction between two or more components. So that can be between two resistors, at a junction, between batteries and a resistor, whatever it is. You would need to go through and label all of your relevant nodes from looking at, kind of recalling what you guys did for exam 2 when you guys got to choose. I think only 1 or 2 people chose the node voltage method. So this one is a little bit on the trickier side, especially when you start having more and more nodes. So it's up to you on what you want to do. But for this one here, right, we have 4 different nodes. We would need to go through and figure out which one is our zero. Typically, this will be done at a place where we don't want values. But right, so determine the number of nodes. Set one node as a reference. All voltages will be relative to this particular one. Assign currents at each node where the voltage is unknown. So you'll have to go through and have all of your different currents. For the node method, this is typically more so used when you only want 1 or 2 values. If you want the entirety of the circuit, mesh and loop, right, mesh and branch tend to be a little bit nicer. But you're using Kirchhoff's current law here for node voltage to go through and solve. And then once you do that, you're going to be able to find the voltages at those different nodes. So Ohm's law for all of the methods here. The other thing I got asked about was current and voltage dividers and kind of when to utilize these. So we covered these all the way back in lectures 6 and 7. So this was the exam 1 material. You've never been explicitly asked to use either of these. They've just been helpful to help us figure out what's going on. So for voltage dividers, this is only used when we have stuff in series. So series only. So here we have an example for that. Here's its kind of definition. Here's the equation that we have. So we have Vx is equal to Rx over RT times Vs. So this here and how this equation is written out is for its representation here, it's explicitly for when we just have stuff in series. This is not always going to be the case. Your circuit on the exam will have series and parallel involved. So in that case, when we're looking at RT, these are just for all of the ones in series for that section we are looking for. So let's call this the section total or resistors in series. Rx is the one we care about, and Vs here is if we only have series, it's the source, but it is the voltage across all of those resistors in series. So in this case, let's say we don't have the Rn here, we would have 3. That would be the voltage drop across the 3 of them. You would use the total resistance across those 3 and then look at the individual one. So you cannot look at it for the entirety of the circuit. If you have a complex circuit where you have series and parallel, you can just look at that chunk of series to go through and apply this. The same idea is kind of true for current dividers. So this is going to be where we have them in parallel only. So series, we have voltage divider, parallel, we have current dividers. So what we have here, right, we have a current, it's getting split between them. We have a similar looking equation because of how resistors interact with each other in series and parallel. The relationship between RT and Rx is flipped. So we can derive these from each other through Ohm's law. But here, RT, this is the total for all in parallel in the section. So here it would just be R1 and R2. If we had a third one in parallel, so let's say we had, this here, then it would be R1, 2, 3. if we introduced another set, let's say we had two in parallel over here without the ideal wire between them. In that particular situation, we would not be able to compare all four of them at the same time because it comes back together and then divides. So anytime we're dealing with the current dividers, again, we need to look at for that particular chunk of stuff in parallel. So this IT here may not just be the total current from the battery, but this could be this is the total current coming into those parallel resistors. So that is everything I got asked to talk about. So if you have any further questions, please be sure to ask.